Nowadays, when you want to make a presentation, you have a lot of options. And this is something that I discovered actually last night while making a presentation. And so I went through a bunch of little different things like PowerPoint, Reveal.js, a bunch of little different frameworks which generate PDFs from Markdown templates and so on. And eventually I found Google Docs. And I realized I can make a presentation there as well. So here it is. And so the way Google Docs works, and I find it as an amazing product, is basically you have a paper, a virtual paper, on which you write lines. But the best thing about this is that you actually get to collaborate with other people which are remote, which are totally somewhere else, which I'm sure everybody here probably already saw. But what actually made me interested and what kind of spurred my imagination is how do these things work, right? And like what's behind the scene? How is this program engineered? How is it designed as a system, right? And so I started thinking about it, and once you see like a couple of programs, you start to see a pattern, and this pattern is most programs, they operate on certain data, right? They don't exist in a vacuum. They have some kind of a data model, and then they process this data. They somehow change it, right? And if you want to model, if you want to express the data model behind the Google Docs, and we want to do this as simple as possible, then we could do this. We could say that if we want to get a data model of a Google Doc, then we have to call some method called doc, which gives us back an object which has a type. And the type is a list of strings. And every string is one line in this document, right? So I'm using Scala syntax here. It's actually, everything I'll be using in this presentation maps one-to-one to Java, and I guess this is something which most people are familiar with. But just in case you didn't see Scala, so a def is a way to declare a method, just like in Python. But unlike Python, it's actually typed, so you have to specify the return type. And in this case, this is just a list of some strings. And unlike Java, it doesn't use angle brackets, it uses square brackets to put type parameters of this list. Okay. So this is our list of strings. This is what describes our data model of a Google Doc. But a data model isn't very useful by itself, right? A program wouldn't be very useful if it only operated on some data. It also needs to somehow interact with its environment. So after it's done processing the data, it has to produce some output. And for a Google Doc, typically what you do is you would take this list of strings, and then you would call a high-level operation called for each, which for every line of this document uses jQuery or similar framework to find an HTML element with the ID editor, and then appends the line to this HTML element. This is how you render, this is one way to render things on the screen, right? But the point here is really that you can use this high-level operation for each on this data. Right? And the way this looks is this for each, when invoked, will sequentially invoke this lambda. A lambda is this chunk of code on the right side for every line of the document, right? And this is the lesson learned here. This is like when data is organized in a collection, then you can provide some high-level operations on the data, such as a for each. And for each is not the only example of a high-level operation. There exist others. So for example, if I have a Google Doc and I want to search the lines which have a specific keyword, then I could use this high-level operation on the lines, which is called filter. So what the filter does, it just returns all the elements of the original collection which satisfy a predicate. For example, if I were looking for lines in this document which contain the keyword usable, and I have a document like this, with 3 lines, then applying this filter would trigger for the first and the third line, and after filtering, I would get a different list. And this is something that I could then display in the UI so the users can see it as a result. But the logic behind it, I'm not actually doing the traversal and the filtering here, it's hidden behind this high-level operation, right? And what's significant about this is that this filter takes a list of strings and returns a list of strings. So it doesn't change the elements inside a collection, just filters them, drops some of them. Here's another example of a high-level operation. It's called map. and as the name implies, it maps, it transforms elements of the collection from one collection to a new one, using some kind of a transformation function, which in this case takes a line, creates a new span element, and then just appends the line into this span element, right? So for example, if you had the statement that to iterate is human, to recurse is divine, this is what the result would look like. And what's special is that it takes a list of strings, but returns a list of HTML elements. So it transforms the elements inside potentially to a different type. Okay. So let's get back to our rendering to the screen, right? What a Google Doc will typically do, it won't just render the contents of the document to the screen once. It will do so many times. It will do this probably 30 or 60 times per second, right? So that means that somewhere in our system, we have to have a source of some events, like ticks, right? We have to have some kind of a system clock. And on every tick, we should actually run this render operation. And one way to think about the ticks is if you enumerate them, these are ticks 0, 1, 2, so this is the amount of time passed since your program started, is to think about them also as collections. And the way you can express this is by declaring a method called time, which returns a new kind of collection, which has the type events of integer. And this events collection is called an event stream. What can you do with this collection, right? If you don't have any kind of API, there's nothing you can do with these events. But the basic operation that you have on this collection is called onEvent. And this onEvent also takes a lambda, and the lambda takes the tick, the current tick since the program started, and then executes some piece of code. In this case, it just calls the for each statement, which does the rendering, which we saw earlier, right? So this is how it looks. And there, if you think about it, there's actually a similarity between a list for which the elements exist somewhere in memory and events which happen sometime. But this is more than just a similarity. I claim that it's an equivalence, because when you think about these two operations that these two collections kind of expose, an event stream and a list, then onEvent is equivalent to for each. It does exactly the same thing. It says, when an element becomes available, apply a user-defined function on it. So for example, you can call onEvent on time to do the rendering. But this equivalence doesn't stop there, because you can also define events on a filter on the event stream in much the similar way as you define it on a list. You just imagine that your events are a sequence of elements in time, and then you might say, if I have time, which ticks at every 1 millisecond, then if I filter this and take only every 16th tick, then I'll get a new event stream, which is called frame. So graphically, it looks like this. So it drops some of the events, right? And from this illustration, you can't really even tell if this is a list or it's an event stream. You can't really take what I'm talking about. So this shows you that actually these two operations are kind of equivalent. And similarly, I can define map on the event stream. So let's say I have some kind of a keyboard and a mouse, specifically a keyboard here. And this keyboard it produces some events. So, and it is represented as an event stream which produces tuples. And these tuples have a boolean which say if the key is pressed or not, and a character which says which key was pressed or not, or released. So if I want to define a new event stream, it's called presses, then I filter the keys for which I pressed, and this is basically telling you, like, for those to whom the first element of the tuple evaluates to true. So I filter those, and then I call a map to just take the second element of the tuple. And what I get back is an event of characters. So this is how you use map on event streams. So you can see really these two things, an event stream and a list, are very, very similar. So if I take a look at my system now, it's basically composed of several things. So we have this document, which is a state of my program. It's in the middle. Then I have this event thing on the top. And I have another events of characters, which corresponds to my keys, which we have pressed. And these things, they operate somehow on this data model. And concretely, what a key events do, they write to the document to add new keys to it, right? So that means they mutate the data model. And on the other hand, the time events, they read the contents of the documents and then transfer them to the screen. So this means that you basically have these events doing read and write on some kind of a shared state. And this is always, when you see things like this, you have to have an alarm. What would happen if these things happen concurrently at the same time? So in other words, when do events happen? When do they actually get to execute? When does this on event thing get to execute? So in this framework, the events execute one after another. They serialize. So there's some kind of a boundary between the outer world, which represents external events to your program, such as a timer or a keyboard, and the actual execution of those events, which operate in your data model. So this is how these concurrency issues have been solved. Basically, when events come into the system, they have to serialize. And when you think about it, most UI toolkits are exactly organized in this way. They say you have a single thread, special thread, which is called the event dispatch thread, which executes the external events one by one. And this is a good idea, because if you have some kind of a common shared state, you don't have to synchronize it. You don't have these problems like data races, race conditions, deadlocks, and so on. So what people often say is that event streams, which exist like a general concept in programming, are an abstraction for asynchronous programming. So you might ask yourself now, okay, if the events need to serialize, then if they have to happen one after the other, how is this an asynchronous programming framework? So asynchronous seems to somehow imply things can happen whenever, including at the same time, right? But actually, asynchronous is very different than something else, which is called concurrent. Concurrent, if you take a look at the dictionary, actually means something is occurring at the same time. And it turns out, something I found out last night, is that asynchronous means not occurring at the same time. So these two things are exactly the opposite. You can have asynchronicity without concurrency. And this is how these events propagate here. So the best thing is to illustrate this on an example. So let's say that you have this external event called time. And then you filter this time to get a frame every 16th tick. And then you install two callbacks on it, like two on-events invocations. One is to use to do your rendering to the screen. The second one is to do some debugging. So basically, you log the fact that the frame has been rendered to the standard output or to the console. So the way that event propagation works is first it gets propagated from time to frame. And if it passes the filter, another event gets propagated here. And then it's actually not defined which of these two on events will execute first. So for example, log could execute first and log something to the standard output. And then the actual contents on the screen could get rendered. And the way you would express this in the code, you would say frame is a filter of time. And when there's an event on the frame, then call the render function. But when you think about this, when you look at this code, you would expect if you see an execution here, for example, you're stepping through the code with your debugger, then in the next step, you would expect this next line to execute. But this would be synchronous programming. What happens instead, that there's another on event written somewhere else in the system, which executes before this event. So they don't happen concurrently. They just happen one after another in an undefined order. And this is what asynchronicity means. It means eventually. It doesn't mean at the same time. Okay, this a small point actually, that this asynchronicity is useful because it allows you to decouple modules in your program. You can decouple rendering to the screen from logging to the standard output, for example. Or you can decouple handling keyboard events from time events. But at the same time, because you don't have concurrency, you don't have to worry about data races. This is the advantage here. But this is not to say that concurrency is useless. Concurrency also has its uses. So let's take a look at the example. Let's put this event stream that we just created, time and frame, into a little, slightly larger context. So typically, in our C system, we will have a part of the program which is called the editor. And editor will have some kind of a shared state. For example, the contents of the document, right? Typically, you want to isolate this state from other threads in the system to avoid any synchronization problem. And the way you express this is by putting this reactor block around a series of statements. This means that statements in this block will never execute at the same time. So for example, if I have another event propagation here, which comes from the keys, I would list it as a statement in this reactor block, and it will be in a part of the same reactor. So they will share state. But then the question is, where do the actual time events come from there? And the answer is, these time events, they come from a different timer within this system, with a different reactor, which is called timer, which is producing these events concurrently and sending them to this editor on the left. And similarly, if you have key events, they're produced by a different special reactor, which registers all the keyboard events from your keyboard, and then sequentially sends them to different reactors. For example, your editor. But the reason why this is a separate concurrent component is because there might be other reactors in the system which also react to keyboard events, and they should execute concurrently. Why would you care about this? Well, for example, if you have a UI, and the UI suddenly becomes unresponsive, for example, you need to render a huge document, and you want to exit your program, if the shutdown hook, if the exit hook were in this reactor, then you would have to wait for a long time until your rendering actually completes before this key event for the exit actually gets handled. So you want to introduce concurrency to improve the responsiveness of your system. You want to actually put the shutdown hook in a different reactor. This is why concurrency is useful in a system. Okay, so obviously we need some kind of a concurrency, but then the question is, how do these different concurrency units, which execute at the same time potentially, how do they exchange information? So how do they send events from one to the other? And the answer to this is they use a construct called a channel. So how do you create channels? To create a channel, you can call a method inside the reactor, which is called open. What open does, it takes a type parameter and returns a pair of an event stream and a channel for that type. So it can only propagate events of that type. And how are these two related? Well, this is the writing end, and this is the reading end. So the owner of this pair will actually get to install on event callbacks and read in this way from the reading end of the channel. And the writing end will typically be shared with other reactors in the system so that they can write values to it, events to it, and in this way communicate with the owner of the channel. So let's take a look at how this works on a concrete example. There's one of the simplest communication protocols, which is called server client. And in this protocol, a client sends a request to the server, and server replies back. It's a very simple example of a protocol, exchange of messages, of events. So in this example, the client will say, our editor will say, give me the contents of my doc. And the server will look up those contents, and then he'll return them back in a reply. Concretely, what the client needs to do it needs to open a new channel of type list of strings, because the data element is a list of strings, so this is what the server needs to reply. When he opens this, he'll create a pair of an event stream and of a channel. An event stream, it will keep locally and watch it, read from it. And the channel, it will pass to the server together with the ID of the document that it's interested in, because every document in the system has a unique ID. And that means that the server needs to have some kind of a well-advertised, well-known channel, which takes tuples of the document ID and the channel on which you can send its replies back. And then it will basically look up the document and send it back. So the way this looks in code, you have some kind of a well-known channel, which is the server, which is something that everybody knows about. And then what the client needs to do, he needs to open a new channel event stream pair, which is composed of updates that it will contain the events coming from the server, and the writing end, the update channel, which it sends to the server. And then, when an update comes on this event stream, it will take the new document and replace the old document with the new one. And then the last thing it needs to do, it needs to actually send the server its doc ID and the channel to which the server can write to. And this is all. This is the server client model encoded in this framework, the client part at least of it, right? Okay, so the server client model is kind of nice, but it's very simple, and it has the downside that if your server dies, if it fails, then your whole system stops working. So basically a server is a single point of failure in the system. And unless you're somebody like Google, you probably can't handle that, because your clients all of a sudden can't use your software. And you don't have engineers on call that might replace this right away. So what do you do then? What are your solutions if you don't want to have a single point of failure in the system? Well, you could alternatively use a more torrent-like kind of system in which every participant has a replica of the document in its own memory. So it has its own copy. And these are distributed across different locations. And then, if the participant A, if the peer A wants to do some change, insert something into the document, then he needs to update his local copy of the document and send broadcast messages to the other participants. So for example, if you had this document here, which is called Better Scala, this is the title of the document, and now these three peers want to collaborate on it, and they want to somehow modify it. Participant A might decide to change the title into Java Better Scala. And so after changing his document, he needs to communicate to the other participants that they need to insert the keyword Java at the location 0. And this is what it does. So this is called a broadcast. A broadcast is a different communication pattern in which the sender sends the same message to multiple target locations. And this is the communication primitive we need to more easily implement this kind of replicated store. So how would we do that in this model? So first of all, for the broadcast, we need to define some sort of an interface. So we'll define a method which says for any given type T that you want to send to other people, give me a set of channels for that type. This means that every participant in a broadcast will have to open its own channel, they will have to share them, and then they can send stuff to each other. And then what the broadcast method returns is a pair of an event stream and a channel for type T, such that if I receive an event on event stream, it means that somebody in the system broadcasted this value. And if I send something to the channel, then it doesn't go to one destination, it goes to multiple destinations, to every participant in the system. This is broadcast. So we have to implement this event stream and a channel pair. So if you take a look at the broadcast a little bit, you'll see that it's very similar to open that we saw earlier. The only difference is it takes an argument, the set of participants, but it returns exactly the same return value. So the way it works is if you send something to this channel, then it gets transmitted to everybody else. And if anybody else sends something to your channel, you will receive it on this event stream, meaning you can call on event on it and then update your doc accordingly. So let's try to implement broadcast. How will we do this? Well, first thing we need to notice is that this set of channels here, targets, is the set of all the participants in the broadcast, including myself, the reactor that is calling this function. So that means one of these channels in this set has to actually belong to me. And if it belongs to me, then I know what its event stream is. So I use a utility function called findSelfEvents, which will just return me those events in this set which correspond to my channel. So this is some kind of an external utility function that I have. Okay, and this is events, because this is exactly what I need to return as the first element of the pair. What I now need to construct is some sort of a channel here, such that its events don't go to a single target, but to go with all of them. So how would I do that? Maybe stepped on a cable. Yeah, it seems so. Ah, it got pulled out. Okay. Should pull a small fence here for the speakers. Okay. So how would I implement this channel here, from which I send events to multiple targets? So first of all, I can call open to create a new channel and event stream pair. So this pair is such that all the messages will go to this event stream. But then I can install the on-event handler on this event stream such that it loops through all the targets and forwards the event to all the targets here, including myself. And then in the end, I just return the pair of these events and this channel here. And that's it. I implemented broadcast. This is how broadcast works. Okay, so broadcast is really cool, but it turns out for our purposes, for the collaborative distributed editor with replicas of data at each site, it is not sufficient. Actually, we need something stronger. And it's not sufficient because it doesn't provide sufficient ordering. And what do I mean by that? Well, let's say that now we have this document called Java Better Scala. And this update message from A to B, which said insert Java at the 0th location, already reached C. So this is what C sees at the moment. However, this message here was very slow. It didn't arrive yet. It just is still traveling through the network. At this point, C, having seen this, this title of the document, might decide that the title is too provocative. He needs to deflate it a little bit. So he decides, I will insert a keyword, a word, isn't at the beginning of the document. So the document will be isn't Java Better Scala, which kind of opens the thing and deflates it. And then he needs to send this update to the other participants. He does a broadcast. The problem here is if this message now reaches B, still before the initial update reached it, then what B will see at this point is actually isn't better Scala. Isn't better Scala. And if this message finally arrives at B, he'll do what it says, insert Java at location 0, and this document will become Java isn't better Scala. So if you compare these two titles, they actually convey a very different message. And they have very different results, right? And from this, A and B might conclude that C is actually some kind of a troll here who's trying to start a flame war, right? But the problem that we have here, that the operations that you do on your data model when you broadcast them, they need to be commutative, and they're actually not. Because depending which you insert at the beginning of the document first, you'll get different results. So we have to change insert in our system so that inserting an element x0 at position i0 and then inserting x1 at position i1 yields exactly the same document as inserting I1 x1 first and then I0 x0. So how do we ensure that? Well, one way to ensure this is to provide unique UIDs. So what you could do is say if you have a document which says better, then for every pair of subsequent letters, you could define a unique ID for this location. And a unique ID means that if this is not one, because, for example, if a unique ID were one, just an index into the current state of the sequence, then if you insert something in front, then this would become one, right? So the unique ID would change if the unique ID were just an index into the sequence. So the unique ID needs to be something else. It needs to be really unique, regardless of how much things you insert or delete into your sequence. Okay. And the good thing is if we ensure that the IDs are unique in this way, then if two participants, A and B, send their insert events at two different unique IDs, then it doesn't matter in which order these updates arrive. It's totally irrelevant. In the end, when both updates arrive, you will arrive at exactly the same sequence. However, if both of these participants send their updates to the same unique ID, you still have a conflict because you don't know which came first. Some might see that A came first, some might see that B's message arrived first. Right? So you need to make unique IDs a little bit smarter than this. And as we will see soon, unique IDs actually have to have, so actually every position in the word has to have a unique ID, not only for this location, but for every participant in the system. So let's see what it means. We'll see that in a second. I just want to show how, so if we had something like this, how could we use it? So basically, we could define a function called CRDT, whatever CRDT means for now, and say this function takes a set of channels. And on these channels, I can transmit a UID, unique ID, and an event D, which represent the insertion into the sequence. And what I get back is a pair of an event stream and a channel. An event stream will emit updates to the list. So every time the list changes, I will get a new event with the latest state of the list. And the channel will be the write again, to which I write normal integers into this list, like indices, and elements, like normal insertion messages. So I want to somehow translate a normal insertion and read of the list into something that uses unique IDs, right? So I need to make somehow this transformation. And here's one way I can do this. So let's say I have the following data structure. The data structure is a tree, and it's an n-ary tree, so it has many children, and it has a basic object which is called just a node. And a node looks like this. So it has one pointer called 0 at the left, and this represents a subtree which has all the elements which precede the elements in this node. And after is the same thing. It's all the elements which come after the elements in this node. And then it has some additional pointers whose value we'll see in a second. And it has some slots. And these slots are currently empty. And this slot here contains the value E. And you can see that the current state of the document just contains E. And this data structure will have the following invariant. So these slots, they're actually indexed with names of the participants in the system. So that what this means is that A can only write to this slot. So it cannot write to B slot. You can only write to your own. If you don't have anywhere to write, then you have to construct another node and write something somewhere else. So let's see how this data structure works on an example. So let's say that B wants to insert the capital letter B before E. Then he looks into the data structure and sees that the only place that a letter could come before E is here in this subtree. So he needs to extend the subtree with a new node. And in this new node, he writes the capital letter B to its own slot. So far, so good. So in the next step, it wants to add a letter T to make the whole word bet. At this point, it takes a look at the root node and sees that T can come after E directly in this slot because it's unoccupied, and this is its own slot. So you can write it here. And now if we want to see the state of the data structure, we just need to traverse this tree from left to right in order. Okay, and we get the word bet. So B, E, T. Now, if another participant comes along, like A, and wants to turn this bet word into better, what he needs to do is first insert T. So he takes a look, where could he insert T between E and T? So then he takes a look at the root node and sees that between these two letters, E and T, there's actually a pointer. So he can extend the tree with a new node and write T into its own slot. And then similarly, E and R, they actually have to appear here on the right. So extends the tree 2 more times with 2 more nodes. And now if you want to read the contents of this data structure, then you need to traverse the nodes in order from left to right. So B, E, T, T, E, R, better. And what's specific about this data structure is an interesting property that every letter in the tree can be assigned a unique ID. And here's how. For example, let's take a look at R. To reach R, we need to follow the pointer 1, then the pointer 1 again, and then at slot A, we see R. Therefore, its unique ID is 11A. Next, if we want to determine the unique ID for E, we have to go right, that's 1, and then read, and then see this is at position A, so therefore the unique ID is 1A. Similarly, here, we follow the pointer A, we end at the slot A, the unique ID is AAA. And finally, if we want to see this element B here, and what its unique ID is, we follow the pointer 0, and then it's at slot B, so therefore its unique ID is 0B. Now I underlined the last character in each of these unique IDs, and here you can clearly see that the unique ID ends with a character which is the name of the participant that originally wrote that element. And this is always like this. And this means that an insert by a process X will happen at a unique ID which ends with X. But if it ends with X, if every insert by process X ends with X, that means that 2 processes X and Y never use the same unique IDs. And if they don't use the same unique IDs, that means that their broadcasts can commute. It doesn't matter in which order they arrive to the destination. So basically, if you use this data structure now, you can do the following. You can create a new channel such that it translates an index in the data structure, in the sequence, and an element to a pair of a unique ID and an element, then use the existing primitive that we defined called broadcast, and broadcast this to all the participants in the system, and then use the receiving part of the broadcast to get updates from the other participants, and then use those updates to update the data structure, and then traverse the data structure and pump it out to the client as just a list of elements. And what's nice now is that the client actually no longer knows anything about the internal implementation here. It just knows the interface, which is give me an index and an element, give me back a list of these. And this is what our system looks like now, because we can extend it. We can say that updates, the event stream from the keyboard, can actually be routed into the CRDT, into its channel, and updates from the CRDT can be used to update our document. And this is how the whole system looks like now. And then the question is, why did I actually show you this very complex data structure called a CRDT, whatever that means? Well, there are 2 reasons. Well, first, we just implemented an online collaborative editor in less than 50 minutes, which kind of tells you that there's some nice properties about the system because it composes nicely and is able to declare these distributed algorithms in a very concise and convenient way. And in fact, if you take a look at all of the code that we wrote here today, including the CRDT implementation that I didn't show, it actually fits into a single slide, which is pretty cool, right? It's a prototype, it's very simple, but it's already something you can showcase to somebody, and it's a working prototype of a collaborative online editor. But there's another reason why I chose CRDTs, and this is that CRDT is just a function, it's just a method in our system that we defined. And if it's a method, that means that you can independently take it out, you can test it in isolation, you can mock it if you don't have its implementation to test the rest of the system, and you can even package it in a module and release it in a library, and then your clients don't need to know anything about the CRDT implementation. They can just import a method called CRDT from an existing library and just integrate it into their editor. And this is something that I claim you cannot do with a traditional actor system. And I don't have time to go into that, but I visit you to take a look at our framework. It's on GitHub. And if you have any questions, I'd be happy to take them. Thank you.